So we're going to do a demonstration of a Schweitzer Engineering Laboratories Model SEL 501 overcurrent relay. This is not a comprehensive demonstration. This is a very capable relay, lots of functionality in it, so we're just going to touch on some of the basics. Now, in a prior video, we talked about the older style electromechanical General Electric relays. Actually, other companies other than GE made them, but the electromechanical style used an induction disc that would spin as you applied an overcurrent condition beyond the pickup value. And that disc, as it would spin, would take time before it closed the trip contact for the breaker. So that would give the overcurrent condition a certain amount of time to persist before we actually cut the power off. That's useful for things like inrush current on motors or for thermal constraints on devices like transformers that can take a certain degree of overcurrent before they actually run into any trouble. So the time overcurrent function is a very basic protective function in power systems. We also have the instantaneous overcurrent function. If we exceeded a certain current value, a certain threshold there, it would trip the instantaneous. The target would appear, showing us we had an instantaneous trip, and that would immediately shut down the breaker with no time delay at all. If we had a time overcurrent event, that's where the disc would take time to rotate, the peg would touch the contact, and then we'd have a time overcurrent. You'd see the target come up for time overcurrent, and that would trip the breaker after that certain amount of time. So again, very quick review of the electromechanical overcurrent protective relay system. What we're doing now is we're going to take a look at the more modern version, this one made by Schweitzer Engineering. There are other companies too, including General Electric under the Multilin brand that makes modern protective relays. This is microprocessor based, so there are no moving parts in this relay. There's no disk, there's no time dial, there's no mechanical targets, but we use a lot of the same terminology. So when you look through the manual on this and you look at the settings, you'll see things like time dial setting or target that harken back to the days of electromechanical relays, but same functions, different implementation. So in this case, we've got a relay that is not only monitoring 3 phases, but also doing it on 2 separate relay functions. So it's actually 2 relays built into one unit, which is why they call it a dual universal overcurrent relay. Relay X and Relay Y, and each one of those has 3 current inputs, phase A, phase B, and phase C. It can also detect reverse sequence current and neutral current based on those 3 measurements. So it's a lot more capable unit than the single phase electromechanical we looked at before, but we're going to test it on 1 phase alone just to show you how it works. In this particular case, we're going to be testing the X relay on phase A. Now to do this, I need to inject a certain amount of current into it to simulate overcurrent condition. Now as we recall, the current came from current transformers. This is the basic sensor device that would go around the power conductor, and when in this case you had 100 amps of current going through the power line, you would get 5 amps of current through the secondary wires of the current transformer, and that 5 amp signal will come down to the relay to activate it. Well, same thing here. We take the output of a current transformer, we run that to the digital relay instead. So instead of moving a mechanical disc, a microprocessor now times the overcurrent event and tells the breaker when to trip. Because once again, these big power circuit breakers, they need to be told by external devices like this when to trip. We're going to be monitoring that. To monitor what's going on, we have a meter here, which is going to measure how much current I put into the device. We're measuring volts AC over a shunt resistor. So we'll pan the camera over here. This is a 1 milliohm shunt resistor measuring the amount of current that I have going through the relay. And so with 1 amp of current going through, I get 1 millivolt of drop. And this permits me to measure fairly high currents with this meter. We also have a Fluke multimeter attached measuring ohms to measure the continuity of the trip contact on the back of the Schweitzer relay. So when this encounters a trip event, we'll close that contact. We'll signify that by the Fluke meter beeping at us. So here we go. I'm going to adjust my current using the Variac transformer. I'm actually powering a step-down transformer, which powers another step-down transformer, creating my low voltage high current to go into the relay. And right now I'm measuring about 3.6 millivolts AC. Now with my 1 milliohm shunt, that corresponds to 3.6 amps AC of current into this relay. So if I come over here, I see a computer monitor that's been connected to the relay, and if I type in the meter command, whoops, here we go. Type in access. I need to enter the password to get into that. If I type the meter command, I see what this relay thinks it's measuring. Right now, the current on A phase for relay X measures as 728 amps. If we go back to this, of course I'm not sending 728 amps into it, I'm sending in 3.6 amps. But remember, this knows it's connected to a current transformer, a CT. And so into this relay, we have programmed that CT's ratio. And I told this relay it's expecting a 1,000 to 5 CT ratio. So 5 amps coming into this will be interpreted as 1,000 amps line current. 3.6 amps coming in then gets interpreted as about 720 amps of line current. I have a little bit of an error on this meter, so if you run the calculations on your own, it'll be slightly off, but that's okay. I need a better quality meter here. I'm going to increase the current. I'm going to increase it until I see a current there at my HP multimeter of about 5 amps. Now remember, the relay is expecting a 1,000 to 5 current transformer ratio. So 5 amps here, 5 millivolts equals 5 amps, should be 1,000 amps in my power line. If I type in the meter command again, I see indeed 1,006 amps coming in on A phase for relay X. Now, my pickup value for time over current was set for 1,000 amps line current or 5 amps CT current. So right now, as we speak, that relay is very slowly timing. If we pan back to the relay here, there's no indication it's actually timing. There's no wheel that we can watch move along. But it is actually timing the event, and it said we do have a fault. New event, a fault on X. So it detects that we're into our pickup range of current and knows there's a fault here. As mild as it is, it's taking its time to time that out. What I'm going to do is hasten this a little bit. I'm going to increase my current so a little bit more than 5 amps. And when we do this, we're going to see fairly soon, we'll get an actual trip on the relay. So we're going to sit here and watch the front panel. We expect to see an overcurrent condition on phase A for relay X. We just give it enough time. Again, we're beyond the line current value that we established for a pickup. We're just waiting for the overcurrent curve to reach its set time, and then it's going to actually trip the relay. There we go. So right here, I have an overcurrent condition. It's flashing the targets at me, so it's similar to having this go orange on the old technology. I just have flashing lights telling me which relay tripped and which phase it was. Of course, our fluke meter over here is beeping at us, which tells us that contact is closed. It's trying to trip the breaker. So now I'm going to reduce the current. When I reduce the current, you hear the annoying beep go away, because as the breaker has been tripped and opened, the current falls to 0 and it's no longer trying to trip the breaker, so the contact opens. But notice it still maintains a record of the trip event. On the front panel, it shows me I had an overcurrent condition on phase A, and that was relay X. So just like the old school relays that had the orange colored targets that would pop up and latch, this has blinking LEDs that will latch. It also shows over here that we had a fault condition. We had a fault condition for relay X, and it shows me what the current was at the time of the trip, 1,243 amps. Remember, my pickup value for the overcurrent was 5 amps on the secondary of the CT, which was 1,000 amps on the line, the power line. And so we're well over our pickup current, and so it sat there at that amount of current until it finally tripped. I can also take a look at the history of recent events. I've been testing this relay several times here today and giving it various fault conditions. Our latest event right here, it shows you the date, which is way off. I need to set that. And the time. Here's the fault on relay X, and it shows up as a target. In other words, it actually tripped on A phase for relay X, and that's what tripped out the breaker. I can get even more detailed event data. If I say event 1, I can take a look at the actual event step by step in time. This is showing me instantaneous values of the sine waves, phase A, B, and C, here as it goes along in a list. So if you wanted to interpret blow by blow what happened to the current at 15 cycles prior to the breaker's tripping, you get a record of it here. This is the kind of rich data you would never ever get from an electromechanical protective relay, but it's easy to obtain from a digital relay like the Schweitzer unit. Then it also reviews the relay settings, showing you where we have the pickup setting values and time delays for all the functions of this relay. Pretty cool stuff, I think. So we come back over here. I'm going to do another demonstration. I'm going to reset the target here, so that's analogous to resetting the target flags on the old mechanical relay. So now everything's back to normal. I'm going to now simulate an instantaneous overcurrent condition. I'm going to put my hand on the variac. I'm going to very quickly turn it up, and so what that will do is provide an even stronger amount of current than we had before going to the relay. And now it's going to be programmed to trip on instantaneous overcurrent. This is where it exceeds a threshold that trips immediately without waiting and without timing. So here we go. Here we go. And we get an instantaneous trip. When I turn the current back down, it stops beeping at me. So right here it says that relay X detected an instantaneous overcurrent condition on phase A and tripped out the breaker on that basis. And so that's a simple demonstration of a Schweitzer SEL 501 overcurrent relay. Like I said, it's a very capable unit. This is a lot more functionality to this than we've touched on here, but just to give you a side-by-side comparison of how these two devices function, what their purpose is, it's an interesting illustration.